So given the function shown, f of x equals x squared minus 4 over x minus 2, we see immediately that at x equals 2, the function is undefined. We know that x cannot equal 2. So in pre-calculus and algebra, we have to say, oh well, gotta go home, nothing to do here. But luckily, in calculus, we're given this really great tool called the limit, which means that we can continue to evaluate this function at 2 by evaluating it around 2, looking to see what's happening as you get infinitely closer to the number 2 or the input value of 2. Also, we know from pre-calculus and algebra 2 that there may be two different things going on here. The function could either, or at 2, you could either have a hole in the function or you could have an asymptote. So you don't need calculus to figure that out, but you do need calculus to figure out what's happening at 2. So let's start our exploration of the limit on this function with what we know. And we know that, in fact, this function has a hole, and the reason for that is since I can factor the numerator and eliminate the problem of the denominator, x plus 2 times x minus 2 over x minus 2. Since by factoring I can eliminate the problem, I know that I haven't made the function defined at x equals 2, but I have definitely shown that there is a hole, not an asymptote, at x equals 2. So let's start to use calculus to evaluate this. First, I've entered the function into my graphing calculator on my y equals, so you can see I've entered that function, and I'm going to graph it first to see what it looks like, just to give myself a little overview of it. Well, the graph certainly doesn't have the shape I expected, but it has plenty of information for me to see very clearly that it does not have an asymptote. Now we want to be careful to make sure that we have actually found the area around 2, and so when I put in the trace function I can see that my x input is not at 2. So if I scroll over, okay, so here I am at 2. Pixels on the graphing calculator don't let me see the whole, but they do show me that clearly there is no asymptote here, which is exactly what we expected to find. So let's look at, we've now graphed it, so we have evaluated the graph, or the function, graphically. So we've evaluated the function graphically. Is that spelled right? I think it probably needs another L. Okay, so there's another way, and the method that we'll use most often as we move along through calculus is that we want to evaluate the function algebraically. Or let's use the same word as your text to keep it consistent, numerically. Which is done by completing a table. So I'm going to make a table of input values and output values. And here in the middle, I want to put 2. I want to see what's happening around 2. So we know that 2 is undefined, so nothing happens there that we can use in a table. But what's happening as you approach 2 from the left and the right, as the graph gets closer and closer? And you can see from the graph on the calculator that it appears to be going toward 2. So as I move down the line, or down the graph from the right-hand side, I seem to be getting closer and closer to 2. And as I move up the graph on the left-hand side, I seem to be getting closer and closer to 2. But let's confirm this numerically. And I'm going to do that using the table function on my graph. So I'm going to go to the table set first, so I can see I've set it already to start at 2 because I want to know what's happening around 2, and so I want my graph to jump up in here. And I've set units of 1/1000ths of a jump from one value to the next, so that I can get really close intervals close to 2. So I can get really, really close to 2. If I used jumps of integer values, then I would only be able to look at 1 and 3 as input values to see what's happening around 2. And we all know lots can happen really close to a value between integers. So if I look at my graph, so I've set my table the way I want it, and now if I look at my table, I can see I've jumped on at 2 and it's clearly undefined. We expected that, but I'm given all of the values coming closer and closer to 2 from the right. So let's go ahead and fill in our table with these values. I'm going to turn off and come back so when you come up, so that you're going to see the values appear out of nowhere. So you can see by filling the table that as I choose values, so I'm 3 thousandths of a unit away from 2 on my input values, then I'm getting closer and closer by tiny increments. That what's happening is the output values are actually getting closer and closer to the value, whatever value this is. We don't really know what that is at this point. So we call this the limit as x values approach 2 from the right. That little plus sign means from the positive side or from the positive direction or from positive infinity, depending on how you want to look at it, of this function. I'm just going to write f of x. Later you'll actually write the function in, but I'm going to write f of x. Appears to equal 4. I seem to be getting closer and closer and closer to the number 4. Okay, so that's what I'm going to write for my limit. So I'm saying that really this function, I'm kind of saying this function exists at 2 and that it equals 4, but I'm using the calculus term of the limit to say that I'm really pointing toward 4. Now I'm going to do the same thing on the other side. I'm going to just scroll up and put some values in from the left-hand side. Again, those are just going to magically appear. So you can see that as x values, input values, approach 2, the output values also on the left-hand side approach 4. So I would say the limit as x values approach 2 from the left-hand side or from the negative infinity direction of the function, it appears to equal 4. So I have a way of discussing what happens at exactly 2 by looking at what happens around the hole, which is a really convenient tool when you're dealing with things that you don't know if they're there or not in the real world. And since we get the same value in both directions, we're able to generalize and just say that the limit as x values approach 2, meaning from both sides, of this function equals 4. And so this would be the solution or the evaluation of a function that heretofore has not been evaluable at x equals 2. Yeah, I said evaluable. I may have made that word up. So let's look at another function. In this case, we want to evaluate f of x equals, or f of x equals x minus 2 over x squared minus 4. So really we're just looking at the reciprocal of the last function. Again, we would determine our restrictions on our domain, and so we know that x cannot be plus or minus 2. But as before, I can use factoring to eliminate a factor, hopefully creating a whole rather than an asymptote. So I have x plus 2 times x minus 2 in the denominator, which cancels with the numerator, leaving me with 1 over x plus 2. In this case, I wasn't really able to resolve one of the values. And so we want to look at what happens to this function at negative 2. So negative 2 is going to be our problem area. So I've set up the graph already, so let's go ahead and have a peek. And so I'm assuming that this is negative 2 because what I have is an asymptote, and I expect there to be an issue there. But just to confirm it, I'm going to trace, get myself kind of close to it, and I see that I'm indeed approaching and then crossing over 2 on the x-axis. Excuse me, negative 2 on the x-axis. So let's evaluate it there. I'm going to go back to my table so I can start. I like the intervals I was using before, but I want to start at negative 2 this time. Okay, so I've set up my table. Now let's go look at the table. So here at -2, I expected to get undefined. I'm not going to write my table out. You certainly will be expected to do that in problems on quizzes, tests, and classwork. But we can see by just looking that as my values approach -2 from the right-hand side, from the positive side, we can see that the limit of this function, as x values approach -2 from the right-hand side, is approaching infinity. We saw it on the graph, and we can see by the rapidity with which the changes on f of x are growing. I go from 250 to 333 to 500 to 1,000, and if I made smaller increments, I would see myself shooting off to infinity. So we can say positive infinity is where I'm headed as I approach -2 on the x-axis. On the other side, we want to see the limit, and usually we don't use capitals. I don't know why I did. So the limit as x approaches -2 from the left-hand side, I'm going to scroll up. You can see that the same thing is happening on the opposite side, except I'm approaching negative infinity. So, because what's happening is because both sides of this function are not approaching the same value, we can't say, we can evaluate it on that, at that value, but we can't say that the limit exists. So what we say in this case, taking this information, is that the limit as x approaches -2 from both sides of this function does not exist. And graphically you can see that it doesn't exist, because in order for us to be able to evaluate it, the evidence around it has to appear as though we are going, or indicate that we're headed toward a single value, and clearly we're not. It's going off to infinity on the right hand side and negative infinity on the left hand side. But let's have a quick discussion about what's happening at the other restriction on the domain, the one that we were able to cancel. So what is happening to this function at x equals 2? Remember, x cannot equal 2, but we can see from the graph that clearly there is no asymptote. And so what we would find if we were to move the table, well, let's go ahead and do that. Let's change our table value to a +2. Keep everything else the same. And so now if we look at the table, we can see that in fact the table appears to be, or the value appears to be approaching 1/4, 0.25 on the right hand side, and the same thing on the left hand side. It appears to be approaching 0.25. So we would say for that the limit as x values approach 2 on both sides of this function equals 1/4 or 0.25. Now we don't really like decimals all that much in calculus. I prefer, I'm old-fashioned, the fractions, but either way you would get the same answer. So I would like you to evaluate with a table and a graph the following function. F of x equals 1/x minus 3. So I'm going to get you started a little bit, because that's what I do.